Good afternoon, everybody. Thank you for attending this second showcase session of the GEO Symposium. So during this session, we will have 5 different pitches. So without losing some time, I will introduce the first speaker, which is Michele Meroni. He is consultant at the Food Security Unit at the Joint Research Center. So please, Michele, the floor is yours. Yes, you can sit.
Good afternoon, everybody. My name is Michele Meroni, and I will talk about the Copernicus for Geogram Validation Service. I will talk on behalf also of my colleagues Felix Rembol and Casimiro Orlowski, who is the lead author of this work. We all work at the Food Security Unit at the Joint Research Center. Next, please. So Copernicus for Geogram is an on-demand support service for agricultural monitoring and map validation. It is part of the Copernicus land monitoring service, and it represents the European one of the European contribution to GEO, and in particular to Geogram. To support agricultural monitoring, it has two main components. The first one is a crop type mapping service, which provides crop mask and crop type maps at 10-meter resolution and area estimates. And the second service, which is the one I will talk about today, is the map validation service, where we validate third-party maps. This is in particular in support to the European Union deforestation regulation for existing commodity maps like cocoa, rubber, and so on. Thank you. So why independent validation is important? Because we know that maps derived from Earth observation have errors. So what we do is we follow a statistically rigorous methods, and we use independent data to evaluate the accuracy, the accuracy and give an uncertainty quantification for a given map. This is important because it's transparent, it's third party, and adds value to the map being validated. And also it strengthens its credibility so that it can be used by stakeholders. In the case of UDR are government, industries, and also public stakeholders. So in a nutshell, probably you already know the UDR. It's a regulation that covers key commodities and specify that to place this product on the EU market, they have to be deforestation-free and legal production. It covers a number of commodities. So far, we work with cocoa, coffee, and rubber. It also specifies a cutoff date, so it has to be deforestation-free from 31st of December 2020. And geospatial data plays a kind of big role in this regulation because we need farm geolocation for supply chain traceability. And we also need reliable baseline maps to evaluate the deforestation risk assessments of the given country. Next, please. The service was activated in the past for Côte d'Ivoire, where we had a general land cover, including a cocoa map. It's ongoing in Honduras and Cameroon for coffee and cocoa, and probably the next one will be again Côte d'Ivoire, but for crop, cocoa and rubber specific maps. Thank you. So in this presentation, we go a bit more in the Cameroon activation. That is what we are working now. We have been asked to assess the accuracy of a national cocoa map at 10-meter resolution based on Sentinel. This map is produced by national stakeholders and with the support of FAO. National stakeholders, including the Ministry of Agriculture, and the goal is to support EU deforestation risk assessment, but also general land use planning. Reference date, it's always that of UDR, so end of 2020. And compared to other activation, we see that this landscape is quite challenging, both for the production of the map and both for the validation, because it's a humid tropical environment with also quite some agroforestry cocoa systems. Next, please. So this service has a workflow. First, we identify the area of interest. Then we specify the sampling, the stratification and the sampling design in a feasibility study. All is public on Copernicus. Then there is a field data collection. Enumerators are equipped with a COBO toolbox. Thank you. To collect the information, so that during the campaign we can check near real time the progress of the campaign, but also the quality of the campaign. At the same time, we do desk-based VHR interpretation, so at submitter commercial imagery. The project ends with the validation, which is both qualitative and quantitative. Next, thank you. A bit more on the sampling design. So, for example, in Cameroon, we use 2 strata, cocoa and no cocoa strata. In both of the strata, we randomly selected the primary sampling units, which are squares of 500 by 500 meters. In each of these PSU, there are 25 secondary sample units with a spacing of 100 meters. And the enumerator are asked to reach each single point and provide information about land cover in a 15-meter radius. Next, please. What we ask to the enumerators, the land cover or crop type identification, so plantation in the case of Cameroon, cocoa, coffee. If there is a plantation, we ask if it's monoculture, if it's agroforestry, meaning that there are shade trees, or it's a mixed cultivation. In addition to that, we want the enumerator to express their confidence that the land cover was there already in 2020. And for this, we want them to record traces or evidence, like the fruits are visible in the cocoa plantation, the trees are mature, and the stem diameter. Next, thank you. And why would we do this? Because basically we have a temporal mismatch between the field surveys that happens end of 2024-25 and the reference year, which was, so basically we have a 5 years temporal gap. In this 5 years, the land cover may have changed. And if it has changed, this has consequence on the disagreement we would find in the validation. So we put in place different mitigation strategies. One is one of the previous slides. We ask for visible signs of 2020 presence. And the second one is that we review all the field pictures in the office, and we compare what they observe with historical VHR imagery. Next. So interpreting VHR in this landscape can be easy. This is a good example of 2 points on the left and on the right. The interpretation for left is wetland, and for the right point is coffee. This is confirmed by enumerator and by field observation. Next. It can also be challenging. For example, these 2 points are in these 2 secondary sampling units are interpreted both as forest, as you see, but the one on the left is actually a forest, while the one on the right, the field campaign, show that there are cocoa planted under the shade trees. Yeah, thank you. Next, so can be challenging. So in general, we see that VHR it's pretty useful because it has several advantages. It's resource efficient. It's basically quite cheap. It increase and scale up the possibility of covering, meaning that we can assess remote or inaccessible area. And in addition, with VHR, we can purchase VHR imagery of the reference year. The challenges are, of course, that it's not a in situ observation. It's a photo interpretation. And also we see that in this, particularly in this landscape, complex canopy structure and agroforestry makes it quite challenging. Next. Again, the example of Cameroon, we collected about 6,000 field observation and more than 24,000 VHR interpreted points. Of those, 2,000 were overlapping with field observation. And this is particularly important to understand the quality of the VHR interpretation, so to see where they are usable, if they are usable, and to what extent. The validation is still pending, but I can show you in the next slide some preliminary result on the first map that was produced by the consortium. On the left, the qualitative assessment, we found, for example, I think it's always useful because we found artifacts along forest boundaries and roads. And on the right, the quantitative assessment. You see the confusion metrics. This is only based on the field data. And on the right, the overall accuracy, which in general can be seen as rather good, 86%. But if we look at the F1 score of Coco, it's very low. It's 40%. Just want to mention that not only with this exercise we evaluate the accuracy, so user and producer accuracy, but we also attach 95 confidence interval to this number. So I think it's pretty exhaustive. You are saying that the user accuracy is 96% and the 95% confidence interval is within 95 plus or minus 0.5. Thank you. Next. So conclusion, independent validation, we think is essential for those geospatial products that have to inform policy. To take decision, the decision maker needs to know the quality and the error rate. If you consider, for example, for risk assessment under the UDR. For a UDR, the temporal consistency of reference data will always be a problem because the reference year is 2020 and we are working now. So we think that mitigation strategies has to be put in place. So we have to consider this mismatch. We also think that hybrid reference collection, so VHR and field data, is very useful. Field data is the base, there is the certain data, but VHR enables scaling up the data collection. Thank you. In these particular settings of Cameroon, cocoa agroforestry remains a challenge. It's very difficult. I mean, if the forest is dense and we don't see through the forest, there's no way we can see cocoa or any other plantation underneath. In general, we think that the validation service of Copernicus for Geogram that is made under the umbrella of Geogram has been very appreciated. And discussion, we started a discussion to continue such service in the next phase of the Copernicus Global Land Program. Next, I think it's done. Thank you. Thank you.
Okay, it seems that we are short on time, so I will recommend to have a question during the next break, if you don't mind, if there is any. I will have one, but I will come back to you. Our next speaker will be Karel Charvat. Karel, if you wish, Karel is the principal for Plan for All and is also part of the program board as this, and is coordinating also some activity on OGC under the data working group, I think.
Agriculture data.
Agriculture. for the data working group of agriculture, and the floor is yours.
Okay. Thank you very much. I would like to thanks to GEO to give me a chance to speak. And at the beginning, I would like ask, do you know this bird which is on the image? It belongs to the most intelligent birds in the world. Yes, so there is a group of these birds, and they are very, very intelligent. They are able sometimes also to repeat some sentences and another, and it inspired us, if we are speaking about intelligence, to the name of this. What about we are speaking? How I can
You just ask. She will do
okay,
it for you.
next. So I think that already today on some sessions there was mentioned huge of amount of the data which is produced, huge amount of different processes. But is it real intelligence if we have some amount of the data, but how people non-experts are able to use this? Yes, if we are speaking about intelligence for all, we need to be able to guarantee that, for example, farmers, public servant will be able to use this knowledge which is now generated worldwide. And can you imagine that a simple farmer is able to provide some complex analysis of remote sensing or another data? This is very, very difficult. And of course, if we are taking some decision, we need also to guarantee some trust and traceability to be able to really answer why we are recommended this, because if we will serve the people with black box, it could be a big problem, and also who will do this can influence of the people to very bad decisions. So we need to be able to explain what is the reason of this decision. Next.
Please turn your microphone off and on to make the
Yes. Off and on. Okay. Okay, better. So, what I am now presenting is something like 2.5 year work where we are thinking how we can do this better, how we can bring this information to the people, how we can support the decision. You will see here a few very simple schemas, which looks very simple, but I have to say that on in the back of every this simple box is very, very difficult development and a lot of discussion how we can do this. So we need to use large language model as some orchestrator, not a source of truth. This is very important, yes, because okay, LLM are trained with a huge number of information, but it is not possible to train with all actual information about Earth observation and other. But these tools are able to analyze the questions, the needs of the people, and transfer this into some process. But it is again very important to be able to manage this process. It is important to look on the technology. Yes, if you are working with LLM, you know that there exists so-called rack where you are able to put the documents, and then language model is not working with our library or what was trained, but is working, if you can tell them, work only with this library. But we can do this also with geospatial data, mainly with vector data. We can put this vector data into some form of GeoRack, and we can then query this data. Okay, we need to in some way to follow what was done, yes, because it will be not good to skip all technology, what was done, yes, all metadata. We need to enhance, improve this, but we need to be able to reuse this, and of course we need to develop something what is able to make some decision, some recommendation. Next. So here you can see some very simple process. user is making some question, and this question is analyzing, and we have metadata. Of course, this metadata has to be enriched. It cannot be use the simple metadata like is ISO 19115 or GeoDCAT. We need to put there much more semantics to be able to recognize. Then we can select the data, make the analysis, and in some form, JSON, we can return the data to LLM, and LLM is able to combine to get the answer. What is advantage of this? That we are not dependent on one concrete LLM. Yes, there exist standard interfaces like Olama, and it is possible very easy to replace ChatGPT with some locally running system. There is huge amount of the system. The biggest amount of very good and very powerful system which is possible to run locally are coming now from the China. Yes, we are testing and comparing many of the systems as possibility to use next. So I already mentioned GeoRack. Another possibility is to, for example, use data cubes, yes, because with satellite data, climatic data, data cubes are very important, and again, it's possible to prepare protocol and define some queries how to ask this data cubes for the analysis and how to receive the answer from the data analysis. And what is also important is not to stay on the level of spatial information. We have a huge richness in the text, yes, and till now the common methods work only on the geospatial data. If you find some good article, you need to sit and to start programming what was done in this article to do this. But now with this new language model, you are able to analyze these different methods, different recommendations, but also legislation. For example, for subsidies, yes, we are able to give to the system the list of subsidies for agriculture, and then the system is already able to analyze this. When farmer is asking what is the best for me, they can look, okay, you have in the map you have such condition, for this condition there are such rules, and you can use this. So this is another advantage to be able to combine geospatial analysis with textual information. Next. You can see the needs for semantics. Yes, I mentioned already the semantics. All this standard metadata system which are used and which can be used as for in Earth observation now. I don't know how it is in China or another part of world, but in Europe mainly stack is used now for this data. It is discussed DCAT, GeoDCAT. Of course, before we work in Europe a lot of about Inspire profile, but we need to enrich this metadata and to put there much more information to be possible to analyze which tools or which data are the best to provide it this analysis. But on other side, we can again use advantage of LLM, because I don't know how it was in another part, but I know that when Inspire was implemented in Europe, people hate to make Inspire metadata. Yes, so it was the big problem to make the metadata. But of course, a lot of metadata you are able to generate with the help of artificial intelligence. For example, I can have the maps, and I can have the textual description of what are meaning, what type of trees I can plant it, and with the combination of language models, I can enrich the metadata and prepare the better tool. Next. So there is some possibility what is possible in agriculture. We start work on this in Polyrural project, but because we would like to guarantee the continuity, we switch also to another project, and we are now also developing this into another project, Focal and Bioclima, where we are looking on climatic things, climatic data, but also biodiversity data, and this methods are possible to implement in many areas, but of course it requires many development. Next. So we have maps. We need to make some alerts. What is important to be able to explain why this is recommended, yes, because this is key for any decision to be able to explain. So we need to have some provenance records about the data, because if we would like to support some decision, it is necessary to know which data was used for this. Of course, it is necessary to make some workflow, and also for with artificial intelligence, it is in any case some, we can say, statistics. So we need to be able also make some assessment of the risk or not correct answer. Next. Here you can see some number of potential users. So it is not only for the researcher or for the technical, but also people without technical skills are able to work. For example, what is advantage that you can use your own language, and I think that in any country, farmers are usually not using foreign language. So if they are able to this analysis with their own language, it could open the possibility. So these are some advantages. Next. The trust is important, yes, because we need to reduce the hallucination. A lot of hallucination we are able really reduce if we are pushing the system use only information which we are supplying. But also sometimes the system is not deterministic and is able to answer twice differently if you are putting the same question. Yes, so there is still now a number of things which need to be solved. Of course, we are testing this on a local scale. We are using commercial systems, but also we are testing some HPC infrastructure, what and how we can run, because some models require different amount of memory, different computer capacity. So we are testing this. Next. Here you can see the 3 projects which now are main developers of this, but we are open, and we are now trying, of course, to find more financing for this, not only in such form. We are trying to attract people from outside. Usually every 2-3 months we are organizing code camps where people have chance to meet and work together, learn what happens new. So if anybody will be interested to cooperate in the future with us, we will be very happy. Next. Here you can see again, it is in some way repeated what we done. And last slide. This is or not last. There is one more. So there is again a repeat what could be done and on what we are working. Next. And if there are some questions, please.
Thank you, Carvel. We don't have time for question now, but I think you will be available to answer during the coffee break.
Yeah.
Thank you. Thank you again. I'd like to invite our next presenter, Masaki Yasukawa. He's associate professor at the University of Tokyo, and he has been working especially in the framework of GeoWork program activities such as the DIAS initiative. So the floor is yours.
Hello, everyone. My name is Masaki Yasukawa from the University of Tokyo. Next, please. Yes, next, please. So, as at first, I'd like to introduce the DS data integration and analysis system project. So that received the support of Ministry of Education, Culture, Sports Science and Technology of Japan. So DS started in 2006. The phase 4 project began from 2021. Next, please. This shows the conceptual diagram of DS. So DS develops various applications using archived large-scale Earth observation data in extra large volume storage with 100 petabyte. Next, please. So this figure shows the real-time application for advancing Earth intelligence, such as flood, drought, dam optimal operation, biodiversity, and infectious disease warning. Next, please. So for water-related hazards overseas, DS developed many early warning systems like this. Blue color is flood early warning system. The project in Sri Lanka began in 2017 and has since expanded to Philippines, Myanmar, and West Africa. So yellow color is agriculture drought monitoring and prediction. So the project in Ghana that I'm introduced today build on experience gained from our project in West Africa and Brazil. Next, please. So UNESCO project titled Development of Integrated Early Warning System for Water-related Hazards in Ghana was funded by a Ministry of Foreign Affairs of Japan. So the University of Tokyo and ICHAM, that is UNESCO Category 2 Center of Japan, collaborated to develop an integrated early warning system. The field observation data was provided thanks to the significant contribution of various institutions in Ghana. Next, please. So Japan side developed tools such as bias corrected rain maps using satellite observation from JAXA, ensemble rainfall prediction, flood monitoring and prediction, and agriculture drought monitoring and prediction. Also, Japan side integrated tools and implemented to the DS. Today, I focus to the agriculture drought monitoring and prediction. Next, please. So agriculture drought monitoring and prediction tools have been developed by Dr. Tsutsui of ICHAM. Next, please. So Japan satellite-based passive microwave sensors, AMSA series, are capable of observing surface soil moisture content continuously over time and space on a global scale. Click. Okay. By integrating the dynamic vegetation model with land surface model, CLV DAS can estimate invisible water such as root zone soil moisture content and vegetation moisture content. Next. Also, since vegetation moisture content is raw material for photosynthesis, it is closely linked to the dynamic growth and yield of crops. Next, please. So, however, because vegetation moisture content and crop yield use different units, they cannot be compared quantitatively. Next. Therefore, by normalizing both variables using z-score, that is drought index widely used in drought analysis. Next, please. It becomes possible to make a quantitative comparison. Next, please. This is a regional scale assessment of agricultural drought in West Africa. On a comparison of z-score for vegetation moisture content and per millet yield, we found that vegetation moisture content is high in 2003 and 2004, but yield were low. Next, please. Upon investing this cause, we found that yields declined in 2003 and 2004 due to a locust outbreak in West Africa. Next, so from this slide, I explain a country scale assessment of agricultural drought in Ghana. So since we are able to obtain detailed agricultural statistical data at the district level from Ghana side, we are able to conduct the following detailed analysis. Next, please. In West Africa, we calculated z-scores for vegetation moisture content and crop yield. Here, forecasting the corn yield, we derived the equation for calculating z-score from vegetation moisture content. And the equations for calculating crop yield from z-scores. So by deriving these equations for 13 districts in Brong-Ahafo state, next, please. So we can estimate annual corn yields. This shows the estimation of corn yields from 2004 to 2017 in the 13 districts of Brong-Ahafo state, which is the most agriculturally productive region in Ghana. So furthermore, by inputting, please, yes, 12 ensemble precipitation forecast into the system, it is possible to generate 3 months seasonal forecasts of vegetation moisture content. This is the 12 ensemble forecast of vegetation moisture content from July to September 2018. Next, please. Using 12 ensemble vegetation moisture content forecast, corn yields in July 2018 for the 13 districts of Brong-Ahafo state was predicted. This showed the accuracy. This is a comparison of estimate corn yield in the Brong-Ahafo state from 2004 to 2018 with actual statistical data. The error is 0.21 ton per hectare as measured by the RMSE. Also, sorry, but please. Yes. Also, it was found that the estimation and prediction were very close to statistical data. Next, please. Yes. Sorry. This. Sorry. Yes. Okay, this is a movie of demonstration of visualization tool for agriculture drought monitoring and prediction. At first, 2025 monitoring LLI, land surface soil moisture, root zone soil moisture are displayed in country level, state level, district level, and mesh level. Also, spatial map of each physical quantity is displayed in time slider. Also, users can view the 3 months seasonal prediction like this. So a hands-on training session titled Training of Experts on the Development of Integrated Early Warning System for Water-Related hazards in Ghana by ICHAM and the University of Tokyo was held in Accra, Ghana on November 2025, and 7 institutions, 57 people participated. So finally, I focused on the introducing agricultural drought monitoring and prediction system in Ghana. So our action plan is to expand the training on integrated early warning system to local staff. And PS will provide ongoing technical support for construction and operation of integrated early warning system by Ghana. Thank you very much.
Thanks a lot. We have time for one question. Michele.
Can you give more information about the soil moisture product from AMSR? So resolution, spatial resolution, temporal resolution, long length of the time series. Thank you.
So, resolution. Sorry.
Yeah, general spatial frequency, revisit frequency. How long is the time series? Is it public? General information about this.
Also moisture indicators. Maybe you can discuss it.
Yes,
Sorry,
more detail
sorry.
after.
Yes.
The answer should be long.
Please. I'm sorry.
Thank you very much. If there is no other question, we can ask our next speaker. Thank you very much.
Thank you very much.
We can ask our next speaker, Miao Zhong, an associate professor of the Aerospace Information Research Institute and member of GeoGlam, to come on stage. And the floor is yours.
Thank you, Chair. Good afternoon, everyone. It's really a pleasure to be here to present our work. I make slight change to the presentation title. I just want to show you how the corporate co-develop national systems with the developing nations. As we all know, food security is still a global issue, not only developing country, but also even developed countries still have food security issues. But in particular, Africa and Southeast Asian are suffering a lot. And the reason, not only climate variabilities, but also there are some political impacts like regional conflicts or some other factors like pests and diseases, drought, also affect those agricultural outputs. And most of the developing countries, the lack of the operational information to make informed decisions to like how to make decision on the food trade, the lack of those information. Next page. And to achieve this, actually it demands timely information, and Earth observation is one of the I would say most effective way to do the large-scale crop monitoring. And that's why many countries try to set up such crop monitoring systems, either the big countries or international organizations, they already have such systems. But for the global south, for the developing nations, the high cost or technical barriers always constrain the developing countries to have these national-based crop monitoring systems. As a lot of agencies or countries already have the system, why not transferring the existing tools or technologies to those developing countries? That's our idea. Try to use the existing methodologies, our platform, to transfer to the developing countries. Next page. And we are operating the CropWatch Cloud, which is also a key contributor to GeoGlam. And it is a satellite-based crop monitoring system focused on maize, wheat, rice, and soybean, 4 major crops, and mainly by using Earth observation data and also in-situ data. Recent years, we also use a lot of artificial intelligence methodologies, deep learning algorithms, or large language model. Our colleague also mentioned this in previous presentation, and then all integrate those information together to provide information services and tools to the developing country. Next page. And the scope of and objective of our team is to provide, I would say, not only the produce information, not only provide the information, but also provide the tools and platforms for the developing countries to enable the informed decision making. And we also work a lot on the capacity building. We want to make the capacity in developing countries more sustainable. And we try to make the platforms as a kind of public goods for the whole society. Next page. And after years of development, the latest version now offers a series of application program interface, which we call API-based architecture, which is easy to extend to include more algorithms. And like users could also contribute to the platform and register their algorithms as additional APIs to make it available either only for themselves if they set to private algorithms, or they can also make it public so that every user on the platform can use. Next page. And based on the whole platform, we've been conducting a lot of capacity building activities over 32 countries, and mostly through multilateral cooperation mechanisms. GeoGlam, China Geo, and also a lot of UN agencies were involved, including FAO. Were involved so that we communicate with developing countries. We conducted the training courses in a multilateral way in different countries. Last year, we also set up a regional center in West Africa to enhance the efficiency of the capacity building so that one training, but more countries can be involved at the same time. Next page. And last week, I was in Thailand and conducting a practical application training for Minister of Agriculture and Corporation of Thailand. And we worked together with Office of Agriculture Economies and develop training courses there. Several local agencies were involved. The whole week, we have a discussion and also training for different algorithms for rice monitoring. Next page. And here comes the main part, how to co-create the crop monitoring system. I would say we go through 2 dimensions. On one part is the data dimension, on the other side is components and model dimension. Next page. For the data, we offer the smartphone apps to collect the data more effectively. So AI technology is involved to pre-process, automatic pre-process of geotagged photos using deep learning network and to process massive geotag photos to get the crop type information to support the crop mapping. Next page. And we also have another field level data and information services tools called Corpus Farmer. So it also uses deep learning methodology to measure the yield without destroying the crops by using the computer vision technologies to monitor the yield. Of course, we need some inputs of the crop variety information. And it also provides field level information in return to the farmer so that the farmer contributes some information. It also gets yield-based information to help them to better manage the fields. Next page. And not only the field data, but also the yield data. We are utilizing multi-source of yield data for developing countries. This is an example for Nigeria. So Nigerian, they have their own Nigerian satellite images. And on the other side, Chinese Ministry of Natural Resource also offer high resolution 2-meter satellite, 2-meter resolution satellite data free of charge to over 30 developing countries. So in Nigeria, we use different source of satellite images, Chinese satellite and domestic satellite from the country, and also international source of data. Next page. And then we have the platform offer open source algorithms. Like one example is to use deep learning methodology to detect the cropland parcels. This is a showcase with colleagues from Nigeria. We work together from co-create field parcel samples to train the model, and then integrate the multi-source of satellite images. We can co-produce the cropland parcel that could enhance the accuracy of the crop monitoring in the country. Next page. And for the model selection, we also respect the priority of the users. The platform itself offers 4 types of crop yield prediction: statistical, or the semi-physical models, like biomass harvest index model. But we always discuss with the national users which type of model they want to use, or which type of model they have experience, so that we make the final choice which type of model they want to use for national monitoring. Next page. For example, for the Thailand, we also discussed together to design the system interface. And like this is one of the slides we discussed with the colleagues from Thailand last week. So the interface, what components they want, and what special units they want to target in the system, and what kind of interface they want to show or to visualize the information for the country. Next page. So every single component we discuss together. And model calibration, of course, the most important part. And this regression graph showing the accuracy that was used based on the baseline model that is currently we use for the global monitoring. Of course, if we want to have very accurate accuracy at the local level, we still need a lot of data from local scales to calibrate the model together. So this is what exactly we work together with them. So we visit the field, we collect the field data together, we use the data to retrain the model, to calibrate the parameters behind the model to have a more accurate result. Next page. And not only the model itself, but also we try to develop an automatic pipelines for monitoring. So this is an example of integration of large language model and the remote sensing model. So we provide interface so that the user can type something like a sentence I want to process or monitor rice areas for this season for specific areas. Then the model can interpret the demands from the users and then call the relevant models or algorithms behind the system, and to generate user needed high resolution mapping. Next page. And by working together, we could refine the baseline data, refine the algorithms, and refine the monitoring units. So this is one example. We work together with Thailand to do the national scales rainy season rice areas, and on top of that, we do yield prediction for the country, so that those information the user from Thailand could access freely, and they can also use internally to write a report in Thai languages to support their own decision making. Next page. Take home message. I think we work together with developing countries from the beginning, from the designing of the interface, from the selection of different models and components, and then we develop it together how to the whole system, from interface, from the model calibration protocol, and also from data collection. We've been conducting these mechanisms in different countries. We work together with NASA from Nigeria. We work together with MAF from Cambodia and other developing countries. And with the customized tools, we provide a series of training courses to make sure the users master the skills and they know how to use the system to do the monitoring. And we also offer some fellowship to make sure the local experts, they get the knowledge, they can be sustainable. This could be sustainable with the local knowledge people involved, so that they can also teach other people in a broader scales. And this is the whole creation, co-creation mechanisms we adopted. Next page, I think the last slide. I just want to also mention that the research is very important in these EO domains. Our institute is hosting one of the journal in remote sensing. Just for your reference, if you are interested, if you have a good paper, you can also try and submit to this journal. Thank you. Thank you very much.
We can allow one question if you want. No, don't be shy. Okay. So you can come at the break. Thank you.
Thank you.
For the last pitch of the session, we will have two different presenters. We will have Francisco Galarraga. Is from the Military Geographic Institute of Ecuador. And we will also have Carl Nettleton, is founder of Open Oceans Global. So the floor is yours.
Thank you. Good afternoon. I'm Carl Nettleton. I'm the founder and president of Open Oceans Global, and we are proud to be a newly appointed associate member of GEO and to be here along with our collaborators from GEO Tierra, Ecuador. We're making a co-presentation today. We'll begin with an overview of the global status of ocean plastic pollution. Okay. That's okay now? Okay. And the status in Ecuador as seen from the perspective of global research. Following that, you'll hear from my co-presenter, Francisco Galarraga, the Geographic and Geomatics Director of the Instituto Geográfico Militar of Ecuador, which we refer to as IGM, and he's also the GEO alternate for GEO Tierra Ecuador. And he'll talk about the work of RUPO, the work underway in Ecuador to address ocean plastic pollution. Also with us today from IGM are Colonel Hugo Fernando Aviles, IGM's director, the center there, whose support we greatly appreciate, and Dr. Martha Villagomez, IGM's geographic evaluator and the head of cartographic technical production, who's shown irreplaceable leadership in this work. And I also want to recognize IGM geographic specialist Ingeniero Ricardo Elizalde, who's been tireless in bringing together local data, regional and national data sets from Ecuador. Let's go slide 2, please. Plastic pollution affects marine ecosystems, biodiversity, and coastal communities on a global scale. According to Pew, 11 million metric tons of plastic reach the ocean each year. It's expected to nearly triple by 2040. 109 million metric tons of plastic are already in rivers and lakes, working their way to the ocean. That too is expected to triple by 2060, and plastic production and plastic waste are also expected to triple in coming decades. Next slide, please. So it's really an international problem, and it's an international problem because it happens locally almost everywhere. In Ecuador, where we're doing our work now, over a 10-year period, according to studies by Florida State University, 30,000 total tons went to the ocean, but 29,000 tons of it actually stayed on the beach. That's 88.6%. So Ecuador is kind of unique in that it's a case study where most of the plastic that leaves Ecuador to go to the ocean stays in Ecuador, and most of the plastic that comes from Ecuador goes to Ecuador's beaches. A little bit goes to Colombia and Peru. A little bit comes from Panama and Peru, but essentially it stays in Ecuador. Ocean Cleanup has done some really interesting information about the rivers. The rivers in Ecuador, 74 of them contribute 1,224 metric tons to the ocean each year. 50% comes from the Rio Guayas, and along with 2 other small rivers in an estuary called Estero Salado, and 10% from the Rio Esmeraldas. And these are 3 of the 1,000 rivers sending 80% of plastic to the world's ocean each year. So if most of the plastic that Ecuador sends to the ocean ends up on a beach, we can locate it and use geographical tools to determine where it came from, so interventions can be implemented to stop it. And that's what Open Oceans is doing in conjunction with our collaborators in Ecuador. We're implementing the Ocean Plastic Pathways Initiative. And here's the premise and why our work is different. While much of the work to address ocean plastic pollution is focused at the international policy level, which is extremely important, our work recognizes that there's only 3 pathways by which plastic can reach a beach. Local beach litter, people actually using the beach and leaving it on the beach. Inland water sources, from whether it's rivers, creeks, storm drains, bringing trash, plastic down to the beaches from inland, and offshore sources, often from fishing industry, other industrial work offshore that's brought to the beaches by ocean currents. Understanding this enables a process of elimination of pathways and their sources. And it also allows us to use everything from local knowledge to satellite imagery to pinpoint, document, and map those sources of plastic pollution in a way so that we can inform policy and make changes together using sources and resources from the local to the international. What about Open Oceans Global? Who are we? We're a solutions-oriented nonprofit dedicated to ending the flow of plastic to the ocean using map-based data to drive change, internationally focused on mapping ocean plastic hotspots, which you can find on our website, curating a digital library of proven solutions and matching them to sources of plastic pollution. We're not interested in just finding the problem. We're interested in linking the best global solutions to those problems to see how we can make change. Linking together ocean plastic experts and implementing, as I've already mentioned, the Ocean Plastics Pathways Initiative in Ecuador. We've also been accredited by the United Nations as an official observer of the UN Plastic Treaty process. You can switch slides, please. While important internationally policy decisions are being considered, we want to shift the primary approach at each beach from local cleanup to local prevention. Ocean plastic pollution is an international problem, as I said, because it manifests itself locally around the world. We've developed and are refining with our partners the geography-based tools with support from those collaborators and ESRI Ecuador and ESRI Colombia to show where the prevention needs to happen, and are working to and hope to replicate this elsewhere in the future. Ocean Plastic Pathways translates into La Ruta del Plástico al Océano in Spanish, with the acronym RUPO. We're proud of that acronym. We have, as a team, have come to really love it, and IGM created a wonderful logo, which you'll see in a minute for us. So if you'll please welcome Francisco Galarraga to tell you the RUPO story. Thank you.
Thank you, Carl. Good afternoon, everyone. It's a pleasure to be here with you today in this wonderful event. My name is Luis Francisco Galarraga Benavides, and I represent the Military Geographic Institute, where the official cartography of Ecuador is generated. Today, I will briefly present the project called RUPO, which is an international country collaboration. It proposes to generate evidence for environmental management and decision-making. GeoTierra Ecuador is leading the first implementation of this initiative. This demonstrates Ecuador's commitment and leadership in sharing geospatial information and promoting international cooperation to reduce ocean plastic pollution. Next, please. The methodology combines official data, geographic information system, and spatial modeling. Through geospatial intelligence, we can identify the pathways followed by plastic waste and determine areas with greater environmental risk. This approach transforms official data into practical information that supports environmental planning, monitoring, and policy development. Next, please. One of the strongest aspects of RUPO is collaboration. Government, institution, academia, international organization, and local communities work together. The idea is very simple. When we share information and knowledge, we can transform official data into real environmental solutions. Next, please. Our mapping approach uses satellite imagery, aerial imagery, and geographic information systems. With this technology, we can identify critical hotspots when plastic accumulates. This information helps prioritize action and resources in the areas with greatest impact. At the same time, strategic partnerships are essential because solving plastic pollution requires collaboration between different sectors and institutions. The initiative expects to expand to more than 50 coastal communities affected by the plastic pollution. In addition, RUPO supports the long-term goal of significantly reducing ocean plastic pollution by the year 2030. The project combines science, technology, and cooperation to generate measurable environmental impact. Next, please. For more information about the initiative and opportunity for collaboration, please contact Open Ocean Global or GeoTierra Ecuador. We believe that through collaboration, geospatial intelligence, and shared responsibilities, we can build cleaner and healthier oceans for future generations. As a final point, I want to thank to my Colonel Hugo Avilés, the Dr. Marta Villagomez, and Ricardo Elizalde in Ecuador for all of the support in this project. Thank you very much for your attention. Okay.
Any question from you? We have one. Please use the micro. Use the micro.
Nice presentation. My name is Genki Trauchi. I'm from Japan. I'm a oceanographer, and I did not see any dot in our island. Is this how do we get involved in this nice program?
As we tell in the presentation, you can contact us as IGM of Ecuador or Open Ocean with Carl.
Thank you.
Later, I can share my contact or Carl his contact, please.
Yeah, because we have a very active program in our region, and I was just wondering, like, how many. I'm pretty sure there will be so many dots in your platform because there are so many people working in our region.
We're always happy to learn about more, and we recognize that we aren't the experts. The experts are in local regions throughout the country. We hope our platform will be a valuable tool to bring more people together to help us solve the problem, help you all solve the problem. Thank you. Look forward to meeting you afterwards.
Thank you very much. Any other question? Yes, Michele.
Curious to know what is the spatial resolution you need to detect the plastic? I guess VHR, but probably even more than VHR.
We are using everything from local knowledge to satellite technology. Some of it just, basically scanning areas that are high likelihood of plastic to see what we can literally visually see. We continue to look and would welcome any thoughts from the audience of new and emerging technologies that would allow us to, with technology, to actually provide different sources than we currently have.
So thanks a lot. If there is no more question, we can make a round of applause for all the speakers of this afternoon and session, and for the technical stuff that was around us. And please take the time from the coffee break to start the discussion.
Thank you.